Okay, welcome to the review session for the second midterm. I guess you know what to expect now after the first one. It will be in week 9, 8 to 8:30 on Monday, Wednesdays and Fridays, all 3 days, as you know. We'll probably open things up at 5 minutes to, as we did last time, and close it actually at 8:31. But anyway, the answers, as you know, have to be submitted on Canvas. And of course, the contingency, if you have problems in submitting, just take a photograph of your screen or put the answers in an email and send it immediately, I guess, importantly, to me. I can decide whether I want to incorporate it or not, but if you don't get it in immediately that has some kind of time stamp attached to it, then that's a problem. The second midterm covers a material starting in week 4. 4.1 was actually accelerations in static fluids, so that's really not on here, but fluid dynamics is Bernoulli in weeks 4 and 5. Control volumes or conservation of mass in week 6, and conservation of momentum in week 7, both linear and angular acceleration. And so individually, the topics, at least for the scheduled exam, are in these 3 areas on the different days. The first one is Bernoulli, which is chapter or weeks 4 and 5, and includes free jets, of course, which can be derived from Bernoulli. Moving reference frames, which we also talked about, I guess, in 5.1. The second one is conservation momentum, which was Monday and Wednesday of week 7, and rotational momentum, which was the Friday of week 7. And so this isn't meant as something that completely encompasses all of the material. We'll talk about all the equations you need, but you can look online to see what other resources are available to you. You need to know how to use them, basically, rather than just know what the equations are. So if we go through the individual material, the first stuff is on Bernoulli, I guess. We know that from Bernoulli we can equate, I guess we should probably draw a diagram first, that within x and z, z is positive upwards, x is horizontal, we can define a streamline. For that streamline, we can define locations downstream and upstream. It doesn't matter actually for this because we haven't looked at energy losses yet. We can define streamline velocities, upstream and downstream, pressures, I guess of location 2, elevations, and cross-sectional areas, etc. for each of the points. And the 2 important expressions, at least for a long streamline behavior, are the pressures at location 1, the elevation head at location 1, and the velocity head, streamline velocity head at location 1, have to be equal to the downstream components of those. So you know this, I'm sure, quite well by now. It's been ingrained in your psyche, I would guess, by now, anyway. And so what we need to do is if we have 5 of these, we can solve for the one unknown we have. If we don't have 5, we can use conservation of mass, which is just that density times upstream streamline velocity times area, is equal to density times downstream velocity times stream tube cross-sectional area. And so if we only have 4 knowns in this and we need to solve for 2 unknowns, we can use this constraint to be able to solve for that. We can use Bernoulli to solve for free jets. Free jet, of course, is when you have a jet issuing out of a container, driven in terms of the height to that particular location, and the velocity just from Bernoulli is 2g times that height, square root, comes out of the v squared term. So we have that also. And we also talked about frames of reference. Frames of reference came in 2 contexts, I guess. Our boat, our normal boat, traveling at some velocity of the control surface with a jet flying out of it at some velocity w. And relative to a static observer, v static, from this we have v static observer is equal to the velocity of the control surface plus the velocity of the fluid that is coming out of the front. And so we can always convert between these different components if we so wish. We have to remember that these are actually vectors, not just scalar magnitudes. They have magnitudes in the x direction, shown here, but they also have magnitudes in the z and the y direction if we choose it to be. And so we can use that interchangeably. And the other component about reference frames was being able to define for Newton's second law, F equals dv dt. If this is, of course, a vector as well, but if we look at just the magnitudes in one component, say in the x direction, then we can write this material derivative, which we call this, as a component which is a function of rate of change with time, which is equal to the rate of change with time plus the other components, which again would be not now with time, but would be in space. And so this one we wouldn't do anything with. This one would be with respect to x. The next one would be with respect to y, etc. And really all that we need to know is that this term is equal to the velocity. And so if you write this out in longhand, this so-called convective acceleration is equal to just the velocity, I guess in x. This would be x rather. So this is the convective acceleration. This is the rate of change of velocity in space. If it's a steady state problem, this is equal to 0. And this is the velocity change, acceleration if you like, that you experience if you're attached to the moving reference frame. And so we've talked a little bit about that in class. But regardless, because Bernoulli works on a convective acceleration, of course this is the term that goes to being the v squared over 2g term in Bernoulli. And so this is the convective acceleration. We talked about conservation of mass. And in terms of that, it really is equal to mass in equals mass out. And if there's any difference between those, there's a net accumulation. And we've often drawn a control volume where we can define in that control volume, again, a velocity going in at an upstream location, a velocity going out at a downstream location. We define a control surface. We define a control volume. And between those, we can write the conservation equation, which I guess is something like density rate of change as a function of volume, of the control volume, plus density times rate of change of volume, plus the sum of the mass flow rate changes has to equal to 0. So these individual terms here represent terms which are sums of density times area times the relative to the boundary flow velocity. We can define it in a dot product, but most of the examples we've done have been just in terms of normal to the boundary, and so we can define that. Again, we can define the relative velocities in terms of these components here. This is always true. And all that we have to be careful with are the changes and their signs, I suppose. So this term is the rate of change of density times volume, which is this. And for each of these, if you look at the rate of change with time, the positive is defined as a density change or a volume change, which is positive. In a standard kind of mathematical derivation of that or definition of that. And the only other thing we have to be at least a little careful about is that these are defined relative to a normal to the boundary vector, which is different on each of these surfaces. So if you're looking at mass rates of change, this velocity here is in the direction of the normal, so these are positive. This velocity here is in the opposite direction, so this is a negative sign that gets attached to this relative velocity that appears in here. So you just have to be careful to account for that. So that's conservation of mass. It really is just the fact that mass rate in equals mass rate out, and if there's any difference between that, then there has to be some accumulation, either by changing the density of the fluid in a controlled volume, static volume, like filling a gas cylinder up, or in changing the volume of a container, maybe by filling up a container with water, like the example that we gave with a beaker. So that's first conservation set of equations. The other conservation equations were conservation of momentum. And dealt with both linear cases, which was what we did in weeks 2 and 3, week 7, periods 1 and 2. And again, we defined behavior in terms of some kind of control volume that we had described. Control volume, pretty straightforward. It's defined relative to an x and a y coordinates, x and z coordinate system. You can imagine having flow velocities across the boundary, which I'll just call boundary 1 and boundary 2. These would have an area attached to them. And we label them in some way to look at those components. And we could also have attached to this some kind of force, since we're solving basically Newton's second law. The velocities are vectoral, and they have direction as well as magnitude, as do the forces. And so if we write that out in longhand in terms of what each of these components are, then we can always write out the behavior in terms of Newton's second law, which is sum of forces are equal to the sum of velocities multiplied by mass flow rates. These are vectoral quantities, and so they have forces in the x direction, in the y direction, and in the z direction for each of these vectors. And likewise for velocity, even though it acts on a scalar magnitude, we've always dealt with it in terms of one component at a time that we can define. Get rid of that. And mass flow rate. And so long as we have those, what we can also do is we can substitute in for this these relative velocities. And so because we're working in terms of Newton's law, we have to look at accelerations relative to some static frame. And so what we can do is we can put this in here, if I come down here, and substitute here. And so the forces in the x direction should be a summation, of course. Sum to a relative to the boundary velocity in x plus the velocity of the control surface, again relative to x, multiplied through by the mass flow rates. I guess we have to be a bit careful with these signs. We mentioned before that the mass flow rate component is positive if it's leaving, negative if it's going in. And so I guess if we work on these 1 and 2 locations here, then this would be, in terms of mass flow rate, this would be negative because it's going in, and this would be positive because it's leaving here, and it's in the direction of the unit normal. So that's our reason for that. But if we look at velocities, because velocities are in an absolute sense, they conform to the coordinate directions. So this is in the positive x direction, so this would be positive. And this would be in the positive, in this particular case, the z direction. So this would be positive as well. But maybe just make the note that this is in the z direction and this is in the x direction. I think you get the picture regardless. The other thing that you can divide these into is that we've only looked at static and steady problems mainly. And so steady means that there's no net volume change. Static, I suppose, means that the velocity of the control surface is equal to, zero. Steady means there's no volume change within this component, which are the only problems we've actually looked at, really. And if that's the case, because it's a steady problem, by definition, the sum of the mass flow rates are equal to 0, because these terms on the left-hand side are 0 by definition. And if that's the case, then if you multiply this, which has to sum to 0, by a constant, then this term drops out. And so if this drops out, or rather, if the sum of these two terms drop out to 0, then you're left with the sum of forces are in the x direction are equal to W times mass flow rate. And mass flow rate can also be written as area times density times W. And so sometimes you can look at this, it's defined only in terms of these relative to the boundary velocities to define it. So that's fine when these two cases are correct. And so in class we did examples with the guy on the jet lev, and we did an example with the vane. Both of these are steady examples. They're not changing in time. Look at it now, it looks like the velocities look like some picture. Look at it 10 minutes later, then the velocities look the same. The one that we did for a moving coordinate frame, which I guess kind of was a third, this was 1 and 2. The third was static and steady. This is also moving. So this equation applies to that one as well. But if you look at any case which is unsteady, then the case that we did was the decapitated gas cylinder. And the idea is that because the pressure in this gas cylinder, even if you're attached to the reference frame of this gas cylinder, with time the pressure here is going to be less in 10 minutes than it was in 5 minutes. The velocity is going to be less in 10 minutes than it was in 5 minutes, or 0 time. And therefore it's not looking the same with time. And so in that case we have to use this full expression. So in that particular case we have to use fx is equal to the sum of these two velocities, in this case written for x or y, whichever you prefer, and multiplied by the mass flow rate, which is again written in terms of this term here. No different. But you have to account for the velocity of the control surface, primarily because this term doesn't cancel out because of this, as we just said a bit earlier. If we have magnitudes of, so you can do two conditions. And so one is velocity of the control surface is equal to 0. And then the question is, what is the magnitude of the force that you have to apply to keep it in place? Or the other one is if the force is applied, so in one case the velocity of the control surface equals 0. What is the velocity? What is the force that you have to apply to do that? Or if the force is equal to 0, what is the velocity of the control surface that results from that? So those are the two end-member cases. Of course, you can look at any intermediate value between that. You could prescribe, for instance, the velocity of the control surface, and you could still calculate what the force would be to keep it at that particular velocity, intermediate to those. And so the reason for mentioning that is if you look at the, well, it doesn't want to do that for some reason, who cares? So what you could do is you can look at the two end-member conditions. So if you look at the force that you have to apply relative to the velocity of the control surface, If you're holding the velocity of the control surface in place, you'll get the maximum force resisting it, and so you'll have some number here. If you look at the velocity of the hose, if you like, I guess we've called it V static. And if the velocity of the control surface is exactly at that velocity, then the force that you will apply in resisting it is zero by definition because of these two. And you'll have some magnitude of change of force between these two. This is the velocity of the control surface. And so if you want to look at the power, you can define the amount of power you have to expend. And power, we often write it as W dot, but that's confusing here because we've used W to represent a velocity. So let's not do that. Power is just equal to force times velocity. And in this particular case, the velocity of the control surface. This is in newtons. This is in meters per second. So top one is a joule. A joule per second is a watt. So if you look at the product of those as force times the velocity of the control surface, again as the velocity of the control surface, at this point here, the force multiplied by zero velocity control surface is zero. This point here, the control surface moving at the static velocity of the jet gives you zero force. So again, this is zero. But if you look at some intermediate value, which is here, it has both a magnitude of the force and also magnitude of the control surface. And so it'll give you a curve that looks like this, which gives you the power. So this is power in these particular units. Okay. So that is for linear momentum. Don't know why this doesn't want to go away. It seems to be stuck there for some reason. So let's just skip down below it. So if we look at conservation of momentum and it's rotational, then you might recall that we drew a similar figure to our sled or our vane. Which allowed us to define a velocity of fluid out of it. We defined a control surface velocity. And now our coordinate system, instead of being the Cartesian one that we had before, is actually around a fulcrum. This here is radius r. This is moving through an angle theta, and it travels at a rotational velocity of omega radians per second. So this is rotational velocity. We can always convert a rotational velocity into a real velocity, which is equal to radius times the rotational velocity. And so these are these angular velocities. This would be w theta. I guess this would be theta as well, corresponding to the fact that it's going around a circle. We can always convert between these in that 2 pi radians a second is equal to 1 revolution per second, RPS, in terms of the convention. And actually, to get the expression that defines this behavior, is all we need to do is we need to take this and we multiply by a radius and a radius. And if we do that, we end up with an expression which is the sum of the forces times a lever arm is equal to the sum of a lever arm, the relative to the nozzle, if you like, velocity, plus the velocity of the control surface, multiplied by the mass flow rate. And so if we look at these, this term here would be the density times the area times the mass flow rate. I guess we could call that 1 if we wanted to. This would be the area A1 along here. So we can always define the mass flow rate. It's relative to the motion of the control surface, which will be attached to this thing here. The velocity coming out relative to the velocity of the control surface, because they're vectors, they're defined in the same direction. And so typically what's different from the previous case, for instance, where we had a vane, was that you squirt fluid in here and the vane tends to move in the same direction. So I didn't write it on here, but this is the velocity of the control surface. This velocity and also the velocity W are all going in the same direction. So that's why these are added. That's why these are also added together to get the velocity relative to static. So in other words, this term here is just Vs. So if you're standing here and it was moving at some velocity Vc counterclockwise, and the fluid was squirting out at 1 meter a second counterclockwise, you add these together, 1 plus 1 would be 2 meters a second, going around the arc as it went around the circumference of a circle. And so for our particular case, what we're interested in doing with that is we're interested in solving it. We realize that typically if there's water squirting out from here, then the control surface will tend to go in the opposite direction from that water. And so there ends up being a negative term in here because one works against the other. And what we can do is exactly the same as the previous case. There are two cases. Well, the two end-member cases, I guess, would be, I haven't put it on here. This would be a force, no, sorry, in the opposite direction. This would be a force in the tangential direction. So that's what this would be. And these two together, this is a torque. In other words, a force times a lever arm, defined as a torque. And so the two cases we can look at are when the torque is equal to zero. Then what happens is that the velocity of the control surface will not be equal to 0. Typically it's a maximum because it's unrestrained and there's no energy loss in the system. And the other end member condition is where you hold the control surface static, in which case the torque that you have to apply to do that will generally not be equal to 0, and actually it will be the maximum torque that you have to apply to keep it static. And of course there'll be a whole bunch of end members in there, when if you want to you can define the velocity of the control surface, and that would give you a torque which you'd like to find. So it's directly analogous. The equation is very similar to the linear momentum equation except for the lever arm and the terminology that we use. And finally, if we look at power, it'll happen in the same way. Power is just defined as the torque multiplied through by the angular velocity. The analog for the linear system, so this is the rotational system. Our linear system, our power was equal to a force times a velocity of the control surface. This is the rotational velocity, of course, of the control surface. So now the VCS is equal to this times omega control surface. So you can convert between them if you need to get power. And so this is velocity, length over time times force. So the units are joules per second, which is watts. Likewise, this is a force times a length times 1 over seconds, which is also the same units, which would be force times, which would be newtons times meters over seconds. In this case, the meters per second is in this term, this is just newtons. In this case, this is Newton meters, and this is 1 over seconds. And of course, you can get any number between here by choosing, no, I didn't need to say that. And that's about it, I think. Yeah, I think. So anyway, so I don't guarantee that these are all the equations you need. I think they are. I'm not trying to trick you in any way. And so have a look at these. Make sure you understand how to use them. It all follows the stuff that we've gone through in class, I think. So you can look at the past Zoom videos to bone up on this stuff if you need to. And I guess finally, just operationally, if you end up in a time crunch or don't get your answers in, then take a photograph of your working immediately and send it, and then we'll sort out whether we want to accept it or not later. Okay, that's it, I think. Good luck on Monday, Wednesday, and Friday of week 9. Okay. Take care. Bye.